All right, so welcome everybody to today's Quasiworld. But now, Ville, you should share your.
Yeah.
So our first speaker today is Ville Salo, and he will talk about groups of cellular automata on groups. All right, so please, Ville.
Yeah. Okay, so thanks for inviting me. I don't do much quasi stuff. I have some quasi isometries in some papers and some course group theory type stuff. And my most recent paper, which I actually wrote after the invite, is somehow has that kind of stuff in it. So I figured it's a natural thing to talk about. And the title of the paper is Word Problems and Embedding Obstructions in Cellular Automata Groups on Groups. So let me start by defining the basic objects. So we want some finite alphabet. So just a finite set A, we usually call it the alphabet. And then we also have a group, and I would like to take a finitely generated infinite group. And let's take G to be generated by a finite, let's say finite symmetric set containing the identity element, if it's important. And then a little more involved assumption that the word problem solvable in polynomial time. I will talk about this in a moment. So there are going to be a few sort of complexity theoretic results which talk about word problems of groups, but there are also results where you don't need to know anything about complexity theory. It's just that the story went that I first did the complexity theory, and then when I took out the complexity theory, I solved two open problems which don't involve complexity theory. So sort of for the story, it is natural to start with the complexity theory. So the word problem is just those words over the generators which equal one, which equal the identity element in the group. Okay. And solving the word problem is the same as saying whether two sequences over the generators represent the same element. So now that we have those things, we can define what is called the full shift. So the full shift is just this set A to the G, so functions from G to A, but we like to think of them as configurations where on each of the elements of G, you have written a letter from A. And this is it's a Cantor space. So there's a natural topology. G is given the discrete topology and A as well. And then you have the product topology on A to the G, where so the convergence is that eventually all of it's a sequential space, and for a sequence to converge, it means that eventually all of the letters are fixed in each position. And another thing about the full shift is that it's a dynamical system. So G acts on it by homeomorphisms, and the formula is just that you move symbols. The symbol at H is moved to GH, which in formula terms looks like this. So it's moving forward, even though we have G to the -1 here. And this is called a left shift. Left shift. So in case my conventions are not the same as yours, G and H for me would be elements of G, and X would be an element of A to the G here. So that's sort of the universe where our cellular automata will act. So the cellular automata are things that operate on this universe, and it's just a group of self-homeomorphisms of this. Or rather, I mean, they are automorphisms of the dynamical system. So you also want that they commute with the shift maps. So I just identify the group element G with the left shift by G. Sometimes people write sigma G for this action, but I am too lazy to keep writing that, so I just say G, and if it's in uppercase G, then you know that it's a shift map. Okay, and so elements of this is called the automorphism group. This is the automorphism group of A to the G, or more precisely, I guess this dynamical system A to the G, where G is acting. Sorry, my G looks like my sigma, but I'm not going to use sigma a lot. So okay, and so elements of this automorphism group are what people often call cellular automata. So the way that F determines the new symbol at G is that it looks to the right neighborhood of G, and it uses some sort of local rule to determine what it writes next. So it has a neighborhood. I will just write NBHD, but neighborhood N. And I use this symbol for a finite subset of G. So there's a finite neighborhood and local rule, which I often write as an uppercase F. And it goes from A to the N to A. And you use this local rule to determine the new symbol. So F of X, if X is in A to the G, then the new symbol at G would be just uppercase F applied to the contents of G uppercase N. Now the problem is, of course, that this is not X at Gn is a pattern on Gn, which is a little complicated, especially if the group has torsion. So more properly, I should write G to the -1 X restricted to N. So you translate the position G to the identity, and then you read the symbol, read the symbols at N. But this is really the pattern at G of shape N. So this corresponds to what people often call cellular automata, like Game of Life and stuff. Of course, for it to be in the automorphism group, it also has to be a homeomorphism, and it's a little non-trivial when this kind of map gives rise to a homeomorphism. But in any case, so that would be the definition. And then I wanted to give a few examples of cellular automata. So first, a sort of trivial example. Let G be in G, and then we define F as follows. So the new symbol at H is just copied from HG. So because we are supposed to commute with the left shift, if you copy from the right, you will commute with the left shift. So this is the right shift. Okay, so that's an example of an element of the automorphism group of A to the G. And then a somewhat less trivial example, which is sort of related to what I'm doing here. Let's take A to be a product alphabet. So this is just a finite set again, and now B and C are themselves finite sets. Then if you have an element of A to the G, then recall that I'm thinking of this as a configuration of symbols from A on the nodes of, or I really think of G as, in terms of its Cayley graph, as a graph where the nodes are elements of G, and then you have edges from between G and GS for all of the elements of S. So you can naturally think of an element of A to the G as YZ in B to the G times C to the G. And I often call these tracks. This is cellular automata terminology. So if the alphabet has a Cartesian product structure, then you have a natural set theoretic isomorphism from B times C to the G to B to the G times C to the G. I'm sure that you see what I mean. The symbol at H is just taken from X, and you split it in these two. Now let's say that E is a Klopen subset of C to the G. It means that it talks about finitely many, positions only. So Klopen just means Klopen, closed and open, but in practice a Klopen set is a set such that to determine whether X belongs to or Z, I guess, belongs to E, you only have to look at finitely many positions, and then you have some sort of rule telling whether you're there. And then you take, let's take also pi in the symmetry group of B. Then you can define an automorphism like this, and I denote it F. F is my name for an automorphism, and it's the automorphism pi given E, and it acts like this. So given a point X, which I split like that into a B part and a C part, at H you just write YH if H to the minus 1 Z is not in E. So that just means that the pattern in Z, sort of at H, does not satisfy this Klopen condition, and otherwise you permute. Okay, so a Klopen set tells you something about it. It checks some property of the configuration near H, and if the C track or the second track satisfies this property, then you permute the first track. Otherwise, you don't. And then this would also this is always in the automorphism group. Okay, so this example 2 is sort of the type of cellular automata that I use in many of my papers, including this one. Okay, and I have used about 12 minutes, which is good. So now, next I wanted to tell you that this group is already complicated. So my paper is going to, in my paper I'm going to be looking at this group, but there are not many papers that have looked at this type of groups, and to explain why, I want to explain to you that already this group is quite complicated, and so I will just tell you a few facts about this group, which are not new.
Wait. A quick question, right?
Yes.
I mean, does the complication somehow come from the choice of A, or for example, if A is just consisting of 0, 1, is this already a complicated group?
For example, 0, 1. You can fix 0, 1 as the alphabet. So all of these complications are basically the same, no matter what the alphabet is. Actually, you have that the automorphism group of A to the Z embeds in the automorphism group of A to the Z, B to the Z. So for any, if the alphabets are different, are non-trivial. So this is by Kim and Rouge from 1990. Okay, so of course there are other things which are less clear. So for example, this is an open problem. Are they isomorphic? So this is an open problem by Boyle, Lind, and Rudolph from 88. Still very much open. So those are some of that's already one of the complications, in fact. But most of the specific complications I wanted to share with you are about subgroups of the automorphism group, because that's something that I have thought about myself. So these are old results of mine. I will just mention just very few. So all ROGs embed in the automorphism group. So here the alphabet doesn't matter because we have this embedding. So ROGs are right-angled arcing groups, or also known as graph groups. And if all ROGs embed, and also subgroups are closed under commensurability, which they are, then this gives you a huge amount of examples and properties already. So a lot of groups are already embeddable in ROGs, at least up to finite index subgroups and supergroups. So this already tells you a lot of stuff. And actually, I've shown that the set of subgroups is closed under countable graph products in general.
So,
and then
a quick question. So I get the understanding that these groups are fairly large, right? Is that right?
Yes. Yes.
So
yes, that's a good.
So are they finitely generated or infinitely generated?
Not finitely generated, but there exists a finitely generated subgroup, which I call POUT, which contains all finitely generated subgroups up to isomorphism. Yeah. So there is a kind of mother finitely generated subgroup, which is a kind of mother group for all the other finitely generated subgroups. I don't know if there's a finitely generated subgroup that contains a copy of the whole group, but all finitely generated subgroups can be embedded here.
And what about the finitely generated subgroups? Are they, for example, do they have exponential growth, or what is the?
Yes. So all ROGs embed, and ROGs include free groups. And then this POUT, because it contains all the finitely generated subgroups. So, for example, it contains the F2, because F2 is a finitely generated subgroup of the automorphism group, and POUT contains all finitely generated subgroups. So, in particular, it contains a copy of F2. So, definitely, the growth is exponential in this subgroup. But there are also subgroups where you have polynomial growth. For example, Z is a subgroup because the shift itself generates a Z. And so I could talk for hours about this group out. Now I wanted to just give you a few hints. And also I wanted to mention, just because I'm going to talk a little about these complexity theoretic notions. This has co-NP complete word problem. And maybe this is maybe at this moment I should give you a quick overview of complexity theory. So let me give you a crash course. So word problems of groups, and I mean more generally languages of any kind, are classified by complexity depending on how complicated it is to check whether a word belongs to the language by a computer program. So 3 classes that I want to mention here are P, which is polynomial time. So just a normal computer, and when you give a word of length n, it should run for n to the d steps before it determines whether W is in the language. Then there's co-NP, polynomial time to check if check a proof of. So we say that a language, for example, a word problem, is in co-NP if there's a polynomial time algorithm where you give some kind of witness or certificate, and in polynomial time you can check whether it proves W to be in the language or not. So obviously co-NP includes P, but it could in principle be larger. And then there's also P space, which is polynomial space. Okay, and then I wanted to give you a few examples just of what kind of things are here. So in the P circle, you would have basically any group which is sort of geometric in some way. So for example, you have free groups, you have all ROGs here, you have the Baumschlag solitar groups, you have the Lamplighter group Z2 wreath product Z, and you have Thompson's V, and many other things. And then co-NP, there are a few things which are known to have co-NP complete word problem. So there's 2 V's in here. So I mean, all of these have their word problem also in co-NP. But when I write it here, it means that it's one of the hardest problems in co-NP. So the true complexity is co-NP. We say it's co-NP complete. Maybe I will say a few words about that. And then this POUT group, which I mentioned here, also lives in this level. And then there are a few automata groups known here.
So what is this polynomial space?
A polynomial space means it's those languages where there is a Turing machine or some kind of computational device which can determine whether a word is in the language after taking at most polynomial space. So it can run for an exponential amount of steps, but it cannot use more memory than a polynomial amount. So for example, a counter to an exponential number can be done in polynomial space because you just have to write polynomial in many bits and then you increase a counter. But you cannot do, you might be able to do, there's also exponential time. There's also, for example, co-next time, which is that you check in exponential time a witness for. Actually, by the way, this should be, no. So these are, basically you don't have to know exactly what these are, but this is the definition that P-space is the problems where you need polynomial space to check them, and P is the ones where you need polynomial time to check them. And in polynomial time, you can use at most polynomial space, so therefore P is at most P space. Maybe I can write this here. And something you need to know is that there's this conjecture that P is not equal to co-NP, and co-NP is not equal to P space. Yeah, maybe I should have reserved more time to talk about these complexity things or not mention them at all. But anyway, for now, this is a super quick crash course. There are these ways to classify the complicatedness of word problems, and this POUT is in co-NP and even co-NP complete, so it's probably not in P. Okay, maybe I should explain. So the word complete here means that if P equals co-NP, then of course POUT will have its language in co-NP. But when I say that it's complete, it means that if P is not equal to co-NP, then POUT is not in P. So sort of complete means that you are on the boundary here. So if they are different, then if the classes are different, then you are not in the smaller class. But if the classes are the same, then of course everything is here. So I should have explained that maybe better. But anyway, it's one of the hardest co-NP problems is what the word complete means. Okay, so then I wanted to also tell you what the limitations are. So what do we know you cannot do with these groups? And this is also an indication that they are complicated groups because we know very few limitations. So we know that the automorphism group is countable. Why is it countable? Because local rules. So every automorphism has a local rule, so therefore there are countably many automorphisms. And maybe I will define something. The rad of F is minimal R such that N can be in here. So for the minimal possible N. So because local rules are usually defined in terms of a subset of the group N, but in the case of if G is Z, then any finite subset is going to be a part of this kind of interval, and then I can take the minimal R so that you're in this interval, and this is called the radius. And the radius behaves subadditively. So the radius of F G is at most the radius of F plus the radius of G. This is something that we will use later. But anyway, so countability is sort of clear. And then there's another interesting thing. This is residually finite. Does everybody know what residually finite means?
Well, the answer is probably no. So maybe you just quickly.
Yeah, okay. For any F, which is not equal to the identity, there exists finite H, a group. There exists a finite group H, and a homomorphism. Let's say phi from the automorphism group to H, such that it doesn't map F to the identity element of of H. So the idea is that if you have a big group, then one way to understand the group is through its homomorphic images, and then residually finite means that with the homomorphic images which are finite, you can separate all of the non-trivial elements. So then it means that also if you have any finite subset of the group which are does not contain the identity, then you can simultaneously map all of them to a non-trivial element of some finite group. But anyway, that's the definition of residually finite, and I can also give you the proof sketch at least. If f is not the identity, then the radius of f is then let r be the radius of f. Then actually the local rule of f, given some pattern like this, where u and v belong to. I will write quickly and then I will explain. So if f is not 1, by which I mean it's not the identity map, which the identity map is the identity element of this group. So if f is not the identity element, then let r be its radius. Now, because f is not the identity map and f is completely given by this local rule, then the local rule must act non-trivially. So if I write the input as being from an interval from -r to r, then the input is basically a word of length r, then some letter, and then another word of length r. And to be non-trivial means precisely that for some such word, you don't map it to the central symbol here. But then f acts non-trivially or on this set p to r plus 1, which is the points which are periodic by this period. So in the case of z, I actually do write sigma usually. Sigma is my generator for the shift. Okay, so this is the finite set of those infinite configurations which are periodic by a period of 2r plus 1. And this is a finite set. Its size is just at most a to the 2. It's actually exactly 2r plus 1. So this is a finite set, and it's easy to see that the automorphisms actually preserve this set. So actually the automorphism group, there's a natural homomorphism to the symmetry group of this, where the image of f is not 1, because this guy acts non-trivially in here, and it extends to an action of the whole group just by just restriction of the natural action. So I mean this group of course has its natural action on a to the z. So you just restrict it to this set, and then that gives you a finite quotient which is non-trivial. And then also we know that this has a co-NP word problem. I don't want to explain the proof, but again it's by local rules. So all of these properties, these countability, residually finiteness, and co-NP, all of them follow directly from the fact that we have these local rules for the elements. So those are the only limitations we know, basically. Or rather, these were the only limitations. In this talk, I'm going to find a new limitation, although it's also directly based on local rules. Okay, so that was just to explain that in the Z case already, this is pretty complicated. So what about other G? Well, now, who in their right mind would look at other G? Well, I don't know, but many people did, or at least 2 people did. So Mike Hochman proved the following. If X is a subset of a to the let's say a to the z to the d, let's say d is greater than or equal to 2, and let's say that this is a nice subshift. Let me define these terms quickly, although they are it's just to be able to state his result. So this is shift invariant. So the left shift invariant and closed, topologically closed. And nice means I'm not going to give the definitions, but entropy should be positive, and it should be an SFT, and it should have dense minimal points. I won't define exactly what these are, but in any case, for some things which generalize this full shift, okay? So you can think of this as generalizations of full shifts. Then the automorphism group of any b to the z embeds in the automorphism group of x. And for a subshift, it's defined the same. It's just the shift commuting continuous functions, and they would just be the restrictions of reversible or automorphisms of the full shift restricted to this h. Okay, so that was Hochman's theorem. And this uses two facts. Z embeds in z to the d geometrically. I mean, like, there's a Lipschitz map from z to the d. That's the first thing that he needs. And the other thing he needs is that z is free. So it's a free group, right? Z is a free group on one generator. Okay, so, and Hochman asked whether the freeness is necessary. If d is less than d, can the automorphism group in dimension d embed into the automorphism group of the smaller dimensional alphabet? He asked this in his 2010 paper. He asked a similar question, but then it's from a conference. Anyway, he asked this question. Okay, and spoiler, I'm going to give the solution. But the other paper about this is by Barbieri and Carrasco-Vargas, I think, and Rivera-Burgos, if I'm not mistaken. And it's from this spring. And they prove that if x to the g is a nice subshift, so in their case it means something called TMP. I don't even know exactly what it means, but it's a generalization of this SFT condition, and maybe there was something else, I don't remember. But subshift means the same. G invariant and topologically closed. And now they need only that the group is not amenable. I actually think that they just need that it contains trees, but I'm not sure. Maybe there was some reason that they really need non-amenability. Then they are able to embed auth F2 in there. So this was kind of the natural thing to do after realizing that Hochman uses precisely geometric embeddings and freeness, because the next free group after Z is the the next group after Z, which is free, is F2. And to be able to geometrically embed F2 in some group, you need that there are some sort of trees, and non-amenability gives you a bunch of trees. Okay, so then they asked, so they asked, does the automorphism group of does the group of cellular automata on the free group actually embed in this one? And so this is a kind of natural question, because, you know, if you were able to embed this group here, then their result is useless, right? So for their result to be interesting, you would really like to be able to say that there is no embedding. And so Sebastian sent me an email about this. I was on paternity leave, and he and so I sort of vaguely thought about this, and I quite quickly, so I started looking at this. So the problem here, so we have these three things to look at. So first of all, this group is countable. That's not going to be helpful because the automorphism group is also countable. So if we have two countable groups, it's probably not going to be helpful for not having embeddings. And then we know that this is residually finite. Unfortunately, this guy is also residually finite. So more is also residually finite. So the thing is that if G is residually finite, then the automorphism group of A to the G is residually finite. That's a general, actually very easy to prove. Very easy to prove in fact, it's proved the same way as we proved that Z in the Z case. This is residually finite, basically. But instead of this kind of periodic point, you have to have a period in the directions of periodicity given by the assumption the G's are okay. So obviously this is not gonna help. In fact, they write in their paper that clearly this is not gonna be helpful. So the next thing I looked at was this. This has co-NP word problem. So maybe the automorphism group of or the group of cellular automaton F2, maybe it has harder word problem. And so this was something that I proved in my preprint. So it has p-space hard word problem. So let me remind you what. So the picture was that. So here we have the automorphism group of A to the F2. So you can see that it's so the automorphism group of A to the Z would be here also, just like Pout. So now you see that this is harder than this. The problem is that the way that things work is that if p space is not equal to co-NP, then this proves that this guy is not embeddable here. But it's only a conjecture that co-NP is not equal to p space. If they so only under this conjecture we have that this guy does not embed. So did you follow that? So anyway, for me this is something that this is a well-known thing for me, this conjecture. So I was quite happy with this. But Sebastian doesn't care about complexity theory, so he kept bugging me and asking if maybe I can prove something stronger and maybe prove an even harder word problem. You can't. So I also proved this, that it is actually in F2 as p space. Yeah, sorry, I'm being very bad about the explanation. So first I proved that it's p space hard. So that's the part that says that if p space is not equal to co-NP, then this guy does not belong here. But then Sebastian was asking me if maybe this guy lives even higher, for example, in co-next time. And my next result was that actually it is in p space, so we cannot get more mileage from complexity theory. And this proof is kind of interesting, or at least it uses an interesting property of F2. So F2 has ball splitting schemes, polynomial ball splitting schemes. So maybe I will explain what that is, because maybe you guys find it interesting. So I start with the ball of radius r. And then I want to split it in two by a set C. So let me write another diagram here. You have the set, BR here, and then I have a subset C. And then I want that the subset C splits my ball into two sets, A0 and A1. So A0 would be here and A1 here. And in the picture, you see that the point is that C is cutting it in half. So all the paths from here to here go through C. That's the I won't write that, but that's the idea. And this C should be polynomial size in this R. Okay. And then I want to be able to also split this into A00 and A01. So I want to find a C. Oh, sorry. I want to find a C0 which splits this into A00 and A01, and then I want to find here a C1 which splits it into A10 and A11, and so on. And then I want that this has polynomial depth. Okay. So at most RD size here, and at most polynomial depth. And for F2, I can take D equal to 0 because, or let's say C, some constant times this. So for F2, because F2 is actually completely disconnected, so it's just a tree. So in there I can just use a finite set for C at each step. And for surface groups, you also have this. For surface groups, you have it for D equal 1, because there you have these paths, these geodesics, which are geodesics can split the ball many times. Many times, sorry. Geodesics can split the ball in half and then keep splitting it in half more and more. So maybe you can tell me which groups admit such schemes. You can find the exact definition in my paper if you want to think about that. So Laurent Bartholdi said that maybe it's true for all hyperbolic groups where the Gromov boundary is one-dimensional. I was not quite able to show that, but might be true. Then I wanted to say another theorem which may be of interest to you guys, because you probably like growth stuff. So I generalized this. If G has stretched exponential growth, so by that I mean that the ball of size r is at least some constant times exponential r to the alpha, where alpha is something positive, then already the word problem of a to the g, the word problem of the automorphism group a to the g is p-space hard. P-space, I'm sorry, P-space. I lost my ability to write apparently. Okay, and so why is that sort of interesting? So the Grigorchuk gap conjecture all groups have polynomial growth of balls or such growth. So one of his many gap conjectures is that you will always either have polynomial growth or you will have at least this much growth. Polynomial means that virtually nilpotent. So in the virtually nilpotent case, you have that the word problem is in co-NP as well. So the point is that this theorem shows kind of a dichotomy. Assuming the gap conjecture, if you have a polynomial growth group, then the word problems of cellular automata groups are in co-NP. But then once you start having this kind of stretched exponential growth, then it jumps to being at least p-space hard. So you need to assume the Grigorchuk gap conjecture, and you need to assume that co-NP is not equal to p-space. But if you believe these two things, then there's this interesting phenomenon where you jump in complexity at some point. Okay. And then what was my next point? Okay. So Sebastian was still not very impressed because he doesn't care about p-space. So then I realized that I have to look more deeply into this slide. So let's look at this again. This guy is residually finite, and this guy is residually finite, but maybe we can find some kind of quantitative version of residual finiteness. Now, I'm not aware of such a thing, but we can invent something like that, and I did. So I have this lemma, which is like quantitative. Let me describe it. Of the automorphism group of a to the z, which says the following: if I don't know why I named the generators, but if you have a finitely generated subgroup and you have a subgroup of H, which is simple, and K contains F, which is not identity, and the word norm of F is at most n, then the size of K is at most C to the n factorial. Okay, so this is a kind of quantitative residual finiteness. So okay, it doesn't actually say, it's very, let's put it in double quotes because it doesn't really say residual finiteness, but let's say this lemma is a quantitative version of the proof of residual finiteness at least. because even though it looks complicated, the proof is extremely simple. So let R be the maximal radius among the generators. Now, if you have an element F, let's forget about this K for a second. If you have any element F which has word norm at most n, then because of the subadditivity, the radius of F is at most Rn, right? Then as we showed in the proof of residual finiteness, we showed that this acts non-trivially on this P2R plus 1, sorry, not P2R plus 1, but P2Rn plus 1. The radius is at most this much, so then we showed that it acts non-trivially here, and then it means that I have a homomorphism phi, which goes from the automorphism group to the symmetric group of P2Rn plus 1, such that F is mapped to a non-trivial element. But then if we assume that K is a simple group which contains F, then it means that K maps injectively. So I assume that everybody knows simple groups, and a property of simple groups is that if a simple group maps homomorphically to another group, if it maps non-trivially, then it actually maps injectively, because there cannot be a kernel for the map unless it's a trivial kernel. And then it means that the size of K is at most the size of the symmetric group, which is at most P2Rn plus 1 factorial, right? So the lemma looks pretty complicated, but the proof is exactly the same as the proof of residual finiteness. Okay? And so now let's find. So then the punchline is that in the automorphism group of A to the F to the 2, we can find huge simple groups with small word norm elements. Okay, but before I don't know if I will have time to explain how to find them. Certainly I will not, but let me tell you the specific theorems I get. So the first one I'm basically already stated, that unconditionally, even if you don't believe in complexity theoretic conjectures, you do not have this embedding. And the reason is, again, in the case of in the case of A to the Z, you cannot have large simple groups with elements of small word norm. And in the case of odd A to the F2, you can. So then you cannot have this embedding. So this shows that the results of Barbieri, Rivera-Burgos, and Carrasco-Vargas are indeed non-trivial. And another interesting thing is that actually I was able to also show this, that the d-dimensional cellular automata groups do not embed in the little d-dimensional automorphism groups if D is at least 3D plus 2. So let me remind you that this was one of Hochman's questions. So Hochman asked if D is less than small d is less than big D, can you have an embedding from here to here? In the other direction, you have a trivial embedding by acting on the cosets. So this solves infinitely many cases of his conjecture. I can. This is being recorded, so maybe this should be beeped. But so I think that I can now drop this to just all pairs where if D is bigger than D, then you don't have an embedding. But I haven't written that yet. But I think I can now prove that after preparing this talk. So anyway, that was most of the things I wanted to say. I will not really have time to explain in 1 minute how we find or what these simple groups look like. So maybe I can just mention another result that I proved, that the automorphism group of A to the lamplighter, this has next time. complete word problem. So specifically, by the way, this is not finitely generated again, but for the purpose of when I say that this is the word problem is like this, I mean there's a finitely generated subgroup whose word problem is this hard. So this is so hard that we know that it's a proper superset of co-NP. So this unconditionally, this is harder than co-NP. So for example, this group does not embed in here just by complexity theoretic reasoning without any conjectures. And this is also, to my knowledge, the hardest word problem that has ever appeared for a sort of naturally occurring group. Okay, you may wonder if this is really natural, but the lamplighter group is very natural, and for me it's very natural to look at cellular automata and all kinds of groups, so it's relatively natural to me at least, but still. Okay, I think that's I understood that 50 minutes was more or less what I'm supposed to talk. So,
okay, yeah, thank you. So let's thank the speaker. And let me open the discussion. So are there comments and questions?
Thank you for the very nice talk. I was wondering if you can explain a little bit what sort of reductions you do and when you prove hardness. What do you reduce to? And how do you prove the hardness?
Yes. So remember that I was talking about these things. So pi given e. So e describes. So I will take precisely a equals b to the g c. Sorry, b to the b times c, and this is used to describe something like computations of Turing machines. And then this guy is the purpose of this guy is mostly to be permuted around. So then you have a Klopen set in c to the g. This describes a huge computation of Turing machine. So the trick is that I have to program in sort of polynomial time or with a polynomial length group element. I have to program a group element or I have to program a description of a Klopen set whose elements describe these huge computations of a Turing machine. So the thing is that a wide, so p space is roughly equal to the existence of trees of computations. So the point is that in here, I can write in polynomial time or polynomial length, I can write a group element which describes this kind of tree of computation, and the tree of computation is basically the same as p space, and that's how I'm able to do the reduction. So this is the kind of thing I do a non-trivial permutation. It has to be an even permutation so that I can do commutator tricks with it, and then the rest is really programming this Klopen set. So there's something called whose theorem? Barrington's theorem. Barrington's theorem is a strong tool here. It gets you sort of off the ground, and in the case of Z, this is all you need to describe the computations. And Barrington's theorem is precisely about constructing such things, although it's in a different formalism usually. So in the case of the lamplighter group, I would take the lamplighter group contains grids, and you can find a grid of size 2 to the n times 2 to the n, which is accessible from basically one node. And then I can say that in this node you permute if the grid that you can reach contains an exponential size computation of a Turing machine, and this gets you to co next time. But unfortunately in F2 you don't have a grid, but you do have exponentially many branches that you can compute, and that's basically p space for you. So in the case of nilpotent groups, you only have a polynomial space for computation, so you can put a polynomial time computation there, but that's really all you can do, and therefore it's polynomial time for these, or co-NP, because of some witnesses arise from the definitions of because it's acting on different configurations, and then the configuration can contain a witness, and that's why it gives you co-NP rather than polynomial time. Okay.
Can I ask a question? Can we go back to this Grigorchuk gap conjecture?
Yes.
So I somehow remember that there was even a stronger version of this, right? Shouldn't this alpha be at least a half or something like this? Do I remember?
Yes.
And
yes.
Okay,
So let me say, there's two things. There is that you are not upper bounded by such a function, or that you are lower bounded by such a function. So as you see, I need that it is lower bounded by such a function. So this is one of his conjectures, but in the case of this conjecture, he doesn't say anything about the specific alpha. But in the other case, which is weaker, where you say you're not bounded, then he says that it should be one half. But I think the Grigorchuk group gets you like 0.57. I don't remember, but I don't think I don't recall if any group gets really to 0.5. So maybe, I don't know if the Grigorchuk exponent should now be the right.
well, I mean, I remember my colleague Igor Pak has all kinds of examples where you actually get all kinds of exponents. So this has been studied. My second question is, you mentioned these conjectures in complexity theory, right? And that these inclusions are still open problems. Could your groups maybe give counterexamples?
So I'm always very skeptical that when you I would say no. I would be very surprised if a resolution of this kind of
maybe we should stop the recording now so that you can speak.
And then I will say yes, of course, but